friction opposes that. There's, again, no internal mechanism in the box to make it go down. There's this external force causing it to move. And so friction opposes that slide. Unlike here, of course, internal mechanism trying to get the feet to move. Here, car, no internal mechanism trying to get the wheel to turn.
Okay, because the horse is applying his feet to the ground. Just
Yeah.
making it go.
And the muscles inside are getting those feet to push backwards.
Okay.
I'm gonna guess that some of you are just going to accept it. Hopefully, a number of you have internalized it. Some of you are gonna keep fighting it. So bring it on. Questions?
I was gonna say, I think one good way to remember it is that since there's nothing pushing that wheel, like an internal mechanism, it would stop due to the friction if it was going to the right, and say the horse just disconnected from the cart. That makes sense, like the friction would make it stop going eventually.
Yeah, there's some complications in that, but I think that works, especially for this one.
What
Yes.
was the original?
Brianna?
Okay, so if a large truck and a small compact
Oh, yeah, back to
car,
there.
if they get into a car accident, I mean, in my head, I've never seen, you know, like a car accident happen in person, but I would imagine that if it was a large truck, like a semi, and like a Prius, the truck could easily just keep moving and just plow through the little teeny tiny Prius. Or
Yep.
a Toyota,
I do not disagree.
so how are they equal?
If we look at this from the point of view, let's first off, let's just assume Newton's third law is true,
Okay.
which we basically are doing for the course anyway, but for right now, just accept that it's true, and let's just see where that takes us.
Is it just
I mean, no, I think the same thing, bodies are wrong.
All right, so I've got 1,000-kilogram car traveling this way,
Like, I'm tired of it.
and a 5,000-kilogram truck going that way. They are cruising along at some constant velocity, and then they hit. I think we can all accept the fact that a 5,000-kilogram truck and a 1,000-kilogram car, the truck's gonna win. And so let's just assume that the truck just plows right through it and the driver of the car, it's done by remote control, no one's hurt in making of this problem.
Yes.
Now, if a force that is being applied is, say, 2,000 newtons. So we're gonna make the claim that so this is the velocity of the car, initial, velocity of the truck, initial. If we do a force diagram, when they are touching each other, I'm making the claim that they're touching each other, so there's a normal force between them. So the car is pushing on the truck this way, and the truck is pushing on the car that way. So some normal force between them of 2,000 newtons. Weight, normal force cancel each other out. So the acceleration of the car, F equals ma, or acceleration is force divided by mass. We'll make to the right positive. The acceleration of the car is 2,000 divided by 1,000, or 2 meters per second squared. Actually, that would be negative. Negative 2 meters per second squared. Negative because it's in that direction. The truck, on the other hand, the acceleration of the truck is 2,000 newtons over 5,000 kilograms, or 0.4 meters per second squared. If the force is the same, as I'm claiming, I am not claiming that they're going to react the same. Because the acceleration, the car is going to accelerate 5 times more or have a 5 times greater acceleration, five times greater change in velocity than the truck will. If the interaction takes place for 1 second, this is gonna lose 0.4 meters per second, and the car is gonna lose 2 meters per second. Obviously, these numbers are incredibly small. So crank up, throw an extra 0 on there, start getting more realistic. So the claim is that the force acting on each is the same. We are not claiming that that the impact is the same. Because the smaller the mass, the greater the acceleration, it definitely is gonna have a much greater change in velocity than this will.
Okay, I get it. That makes sense.
Okay. So it is possible to still be logical when doing this.
Yeah.
As I was doing this question, I also just thought about breaking point for why the smaller car would have more damage, because it likely would have less, like a lower breaking point than the huge semi would. So therefore, it would have more damage for more force.
Oh. Yeah, I think also physically cars are designed for the hoods to crumple and trucks just don't. I don't know if trucks have a crumple zone.
We put a crumple zone on the test, will you accept it?
I will assume that is the part of the vehicle that is designed to
It's crumple.
crumple so that the person takes less impact.
It's in the manual.
But in essence, from a physics point of view, it extends the time of contact, making the acceleration less ultimately. Now, some vehicles, or some objects, so let's take it, you're driving a truck along and you hit a bug. So now, well, it won't be 2,000 newtons, it'll be more like 2 newtons.
Okay, so wait, is that the same?
Pardon?
Would that be the same?
It's the same situation. A bug hits your windshield.
Yes.
Now,
So the force exerted on,
each is the same,
but the reaction is not.
correct.
Okay.
The vehicle doesn't really notice, because if we get down to 2 newtons in a 5,000 kilogram object, that's incredibly small acceleration. In other words, the velocity is not changing significantly. Whereas the bug, we've got 2 newtons over, I would say 100 gram bug is a pretty big one, but a 100 gram bug, that's 20 newtons of, oh, sorry, not 20, that's 20 meters per second squared acceleration on the bug. Very significant.
So is there a case you can think of, like theoretically, where they would not be the same?
All right, you wanna go there?
Yeah, we're going there.
Dang, he said you wanna go there.
All right, so here's where some theorists have speculated that there's an exception. Actually, there's 2 places.
Okay.
When I was in grad school, there was a theory that electrons can exert a force on themselves. So I have not seen anything about that in the last 20-some years, so I don't think it ever came to anything, but there was speculation that electrons could somehow exert a force on themselves. So that would be, the equivalent would be if I could exert a force on myself, that means I could stand on ice and somehow push myself, without moving my feet, push myself off to the side, which is not gonna happen. The other place, which is more likely to be an exception to it, comes down to how does one object know another object exists? So I've got a gravitational pull on me. If I step off the table, I'm going to fall. How does the Earth know that I'm there to pull on me, or how do I know the Earth's there to pull up? The way physicists dealt with this is they looked at it and they said, well, there must be some signal being sent back and forth. And so, since no message can be sent faster than the speed of light, and we can talk about those exceptions also that theorists have come up with, but no experiment to actually test it. So, massless particles should travel to the speed of light, and it's theorized that something called a graviton is what the signal being sent back and forth. So, if I'm a far distance away and I send the signal of a graviton, and it's sending gravitons out, and somehow this communication is between, on the exchange of gravitons. I consider my graviton and then move farther away, and so if that's the case, then it's gonna get the graviton before I do. And so there'd be that moment before it catches up, the signal catches up. That would be the exception. I don't know if you're glad you asked or not, but for the sake of this course, there are no exceptions.
Okay.
That, even when I was working on my PhD, that was not even in the realm of it. That was not considered. That is an extreme case that the theorists deal with, because they're not bound by an actual physical object.
So these laws are true.
Yes.
Okay.
These laws will put a man on the moon.
That's fair.
There's gotta be some validity to it. I think it was one of the problems, it's one later on, where when they talked about space travel, and there was a reporter who thought it was a ridiculous idea because you need to push against something. And so what is the rocket gonna push against in space? Well, it's basically pushing fuel out the back, and so as it pushes fuel out, the fuel pushes back on the rocket, and that's what actually propels it forward. I think, why don't we take a break? Come back, and I'll either answer more questions, or we'll see if we can actually make Newton's second law work.
Do we not have a lab today?
Now, I'm gonna sort of do a group demonstration lab.
What's this one?
That's for Thursday.
Oh, okay.
If you already printed it out, you're ahead of the game. You can sit back and laugh at all the people who haven't done it yet.
No, I'm not. I'm checking.
You just pause it.